Hello everyone, welcome to the next lecture of MOSFETs. Let me give you a very quick summary of what we talked about in the last lecture. We talked about the physical structure of a MOSFET and we discussed its basic operation. Here is the physical structure of a MOSFET. This particular MOSFET is an NMOS or an N-channel MOS. Terminal, source, gate, and drain. Body is usually there, which is connected to the source here. So what do we do? The source and the drain are N-type materials with majority charge carriers as electrons, free electrons. The substrate is P-type with majority charge carriers as holes. So what will happen when we apply a gate to source voltage, VGS? So when we apply a gate to source voltage, the gate electrode, the positive charge accumulates here. This will repel the holes, the majority holes in the P-type substrate. So it repels it and it ended up creating this depletion region. So in this channel region, this will become depleted of the holes entirely. At the same time, this positive gate electrode will also attract the majority electrons from the source and the drain, and these electrons will start to accumulate in the channel region. And once sufficient electrons will be accumulated in the channel region, this process is known as inducing a channel or creating a channel. Now, why this particular transistor is called as an NMOS? Because we ended up creating an N-type channel, right? Where the majority carriers in this channel are free electrons here. In contrast, we will discuss later, in a PMOS, the substrate will be an N-type and the channel will be a P-type. Okay, so this is where we were at last time. So we are going to talk about in this lecture we're going to derive some of the equations. We're going to talk about the conductivity of this channel. And we're going to discuss more about this channel in this entire lecture. Okay, so if you will look closely over here, this channel seems to be a parallel plate capacitor, right? We have a positive here, and then our channel is we have a lot of these free electrons here, right? It's a negatively charged, and in the middle this is our dielectric or an oxide layer in particular here. So this ended up similar to kind of a parallel plate capacitor. Okay, so and we will so let's talk more about a parallel plate capacitor. So our gate to channel, so right, so we have this gate electrode, and then over here we have this channel, or let me put this simpler over here, right? So you have positive here, negative here, and this is your dielectric. This oxide is your dielectric here, right? So this becomes similar to a parallel plate capacitor. And again, this is your gate and this is your channel. So your gate and channel will behave as a parallel plate capacitor, in which the oxide layer, in our case it is silicon dioxide, but that will act as a capacitor dielectric. We talked about this. Then when we apply a gate to source voltage, this will accumulate the positive charge on the gate electrode on the top plate of the capacitor, which is essentially this one. The corresponding negative charge will be accumulated in the channel, which is because of the free electrons. We discussed also this thing that this negative charge is accumulated when we apply a gate to source voltage, and that exceeds the threshold voltage as well, right? So this is also what we discussed in the last lecture. We're gonna talk more about this as well today, that the gate to source voltage needs to exceed a certain voltage to induce a channel, which is called as a threshold voltage, VT. Okay, so this is behaving like a parallel plate capacitor. Okay, so essentially what will happen is an electric field will develop that will control the amount of the charge in the channel, right? So it also determines the channel conductivity. So as this parallel plate capacitor is formed, electric field will be developed, which will change the conductivity of this of this channel. So that is why it is called as, so early in the last lecture we have been using this term, right? MOSFET, again MOSFET, metal oxide semiconductor field effect transistor. We briefly hinted on the what does that mean, field effect transistor. So this is why it is called as field effect transistor as well, right? So we ended up generating an electric field that is determining the conductivity of the channel. Right, so the current that will flow through the channel when the voltage VDS is applied, that's why it's called a field effect transistors. Okay, I'm gonna discuss about this VDS thing just shortly, and then I will come back to this field effect again. So essentially, what will happen is, we kind of briefly touched upon this in the last lecture as well. Once this channel is induced and we ended up accumulating these charges, negative charges in the channel, if we apply a small VDS here, in which the drain is positive compared to the source, what will happen is this was going to start attracting all of these electrons. So when these electrons will be attracted, a current is going to flow from drain to the source, right? So when we apply a VDS, this will establish an electric field between the drain and the source terminal. So this electric field essentially will conduct the current. So that is why this is known as a field effect transistor. So when we apply a VDS, we're going to come back to this point in more detail. Okay. So let's talk about another terminology that we're going to use very regularly in this lecture. That is called as an overdrive voltage. You can also say it as an effective voltage. So by now we talked about this, that at the gate terminal, again going back to this picture, at the gate terminal, our gate voltage, which is gate to source voltage here, our voltage that we give it to the gate terminal, it needs to exceed a voltage, threshold voltage, to induce a channel, right? Okay. So before so until it, if your VGS will be less than VT, no channel will be induced, right? So there we are going to coin now another term that is called as a overdrive voltage. You can call it as an effective voltage, right? So once the VGS, the input voltage to the gate terminal, will reach the VT, this channel induction or creation of a channel process will start. And now as we increase more and more VGS, it will accumulate more and more charges, thereby increasing the conductivity of the channel, right? So VOV, this overdrive voltage, can be defined as the difference of the gate to source voltage minus threshold voltage. So this is, so, or in other words, this overdrive voltage, VOV, is overdrive voltage. So this means that this is this extra voltage beyond the threshold voltage that we are applying to the gate terminal, and increasing that extra voltage beyond the threshold voltage, which is overdrive voltage. So increasing that overdrive voltage will increase the charge accumulation and in turn the conductivity of the channel. We are going to derive specific relationships for that. Okay. Okay, so overdrive voltage is this extra voltage beyond the threshold voltage. So we need a specific threshold voltage to create a channel. So the voltage across the oxide is uniform and is equal to the VGS. Now, another important thing to notice over here is that, and this concept will come in handy in the next lecture when we're going to talk more about the VDS in detail. Okay, assuming right now over here that the VDS, this thing is grounded, and we have applied the gate to source voltage, you will realize that the potential difference across anywhere along the channel or in between the gate and the channel is the same, whether this is at this end or whether it is at this end. So the potential difference at any of these points along the channel length between the gate and the channel is the same, and it is equal to the gate to source voltage that we have applied when the drain terminal is grounded. We are going to discuss more specific cases in the subsequent lectures when we will apply a very small voltage at the drain terminal and when we apply a large voltage at the drain terminal. We will discuss it in more detail. Okay. Right, okay, so the voltage across the oxide, this is what we just talked about, that the voltage between the gate and the channel is uniform across all the points along the channel and is equal to the gate to source voltage. We also define this effective voltage, right? and or overdrive voltage, this is this extra voltage beyond threshold voltage, that will help even increase the conductivity of the channel or more charge accumulation as well. So overdrive voltage is defined as VGS minus VT. Okay, so let's define what is the magnitude of the electron charge that will be accumulated in the channel, right? So we know that from your PE, Q is usually equal to the CV, right? So it has to do with the voltage, it has to do with the capacitance, it has to do with the charge. So what's the total charge that will be accumulated is given as here. This is the magnitude of the charge. It will depend on the capacitance and the voltage, right? So it will depend on the overdrive voltage. So the greater VGS you will end up putting in, you can also write this VOV as VGS minus VD, right? So if you will increase the VGS or the overdrive voltage, your charge accumulation will increase, right? And the second quantity depends on the capacitance, right? So more capacitance, more charge accumulation. And specifically over here, the Cox. So what is the Cox? This Cox is the capacitance of the oxide layer per unit area. And this area is a cross-sectional area of the oxide or the channel over here, which is the width of the channel and the length of the channel. So Cox is the oxide capacitance, right? So this is the capacitance of the parallel plate capacitor per unit gate area. And over here, you can write it as farads per meter square. People also define it as farads per micron square because the dimensions of the W and L are very small in microns, or less than a micron actually, much less than a micron. And then W is the width of the channel, L is the length of the channel, right? So the charge accumulation in the channel can be defined by this relationship, which depends on the overdrive voltage. So greater the overdrive voltage, greater will be the charge accumulation, and greater will be the capacitance, greater will be the charge accumulations. We are going to discuss this term in much more detail, right? So what will happen if we increase the width of the channel, if we increase or decrease the length of the channel, if we increase or decrease the capacitance of the oxide layer. Okay, we're going to talk more. Okay, so let's continue with this. So our oxide capacitance can also be represented by over here. So from again PE, if you are interested in driving this equation, we know that A epsilon over D, you must have seen this equation multiple times, right? So you can also do this C over A equals epsilon over D, right? Over here, in our case, in our parallel plate capacitor on this NMOS or a MOS transistor, our D is essentially the thickness of the oxide layer, and epsilon is again the permittivity of the oxide. And this C over A is essentially this Cox, which is a capacitance over the cross-sectional area of the gate and of the channel. Okay. So we have a Tox over here is again the thickness of the oxide layer, which is the silicon dioxide in this case. And then epsilon ox is the permittivity of the oxide layer. So for the silicon oxide dioxide, our relative permittivity is 3.9. Then we have free space permittivity. So this is you can find out this value. So in most of the questions in the exam, in the homeworks, if you will be specifically told different material, you can assume it to be a silicon dioxide. It is one of the commonly materials used in the fabrication of the MOS transistors. However, if whatever the material will be given, we will provide the value for the epsilon R. For that. Okay, so this is the total this is the oxide capacitance per unit area, cross-sectional area. Okay, so for example, and what does this depends on? What does this Tox depends on? This is the oxide layer thickness, right? And we are going to discuss more and more detail about multiple times. This topic is going to come up in the subsequent lectures. So this is how thick can we make the oxide layer, right? And what factors does it depend on? But over here we can see that what will happen if we will increase the oxide thickness, the capacitance will decrease. And we know that, going back to the previous slide, If the capacitance will decrease, the charge accumulation will decrease, right? So the conductivity will change or decrease. So that is why selecting all of these parameters is critically important while designing these transistors. Okay. So for example, another important factor that it will depend on is your fabrication processes. In this course, we are not going to talk about specifically what fabrication processes are needed in particular or how to actually fabricate these transistors, a topic of another entirely a different course. But important thing is that this oxide layer thickness, what thicknesses can be achieved by different fabrication processes, can be determined by the process technology or the instruments that we used or the fabrication processes that we have available. Now, as an example, for example, if we can achieve a thickness of 4 nanometers for an oxide layer, the total capacitance of the oxide will come out with this, right? So you have 3.9 epsilon naught divided by, this is the oxide layer thickness. So I'm using this equation over here. So this will be the total values. Some people also like to express this in micron square. Micron square just because that, of course, your W, you will realize that the W and L, the other parameters are in more micron, some micron ranges. So that is why people also like to express it as a micron square. Okay. Now let's consider another example. Assume that we are fabricating a MOSFET transistor in which the channel length is 0.1 in microns, right? And then which is 180 nanometers. And our channel width is 720 nanometers or 0.72 microns. So what will be the total capacitance between the gate and the channel? Right, okay, so what will be the total capacitance between the gate and the channel? We know that Cox, what was the total C? C was Cox into W over L, because this Cox was per unit area. So if we will multiply this with the width and the length with the Cox, we can determine the total capacitance between the gate and the channel. So the total capacitance between the gate and the channel will be Cox. Again, Cox can be determined from using this equation on the top. Epsilon ox, over here you can assume again it to be a silicon dioxide. And the thickness of the oxide layer to be, I guess we are just using this, so the thickness of the oxide layer is 4 nanometers over here, so we have it over here. Then our length of the channel, width of the channel, so this is the total capacitance between the gate and the channel. Okay, so in terms of the total charge accumulation by the channel, as we have talked about, we can vary these parameters, right? We can increase the width and the length or increase the capacitance to increase the charge accumulation in the channel. And in order to increase the capacitance, we have to decrease the oxide thickness. So we may have different fundamental limitations as of the current technology, that the smaller dimensions that we can fabricate the transistors with. We're going to briefly discuss that as well in the subsequent lectures. So okay, so again, in short, in order to vary the charge accumulation and in future channel conductivity, we can do it by this capacitance or by this overdrive voltage, right? So as we apply more and more overdrive voltage, again, overdrive voltage is this effective or extra voltage beyond this threshold voltage, right? VGS minus VT. So if we will increase more and more VGS beyond VT, so that will help accumulate more charges in the channel. So we can also increase the charge accumulation in the channel by increasing the overdrive voltage. So as VOVs increase, the magnitude of the channel charge increases as well. Right, okay. And when we increase the charge accumulation in the channels, the depth of the channel will increase, or the channel will become more and more deeper. In this earlier cases, for example, over here in the earlier picture, we have seen this as a very uniform rectangular channel. In the subsequent lectures, we will also see, and I think this depth of the channel idea is going to become more and more clear in the subsequent lectures. When the channel will no longer be uniform, when the channel will no longer be a rectangle, but the channel is going to start to become tapered. So we're going to discuss that. and then we will realize it why this depth is changing. Right, for now, this is a uniform channel or a uniform depth, and this overall depth will increase with the increased charge accumulation or with the increased increase in the overdrive voltage. Okay, so next, so now let's assume our next thing. So now let's assume that we have created a channel. We have applied, and I have hinted upon this topic in the last lecture very briefly, and now we are going to discuss this thing in detail. So assume that this is again our NMOS. I guess that's okay. We ended up putting a smaller VGS, not beyond VD, of course, to create an inducer channel. So we have a gate to source voltage here that ended up inducing a channel. So what will happen? So we ended up accumulating a lot of these electrons here. So a channel is induced, but no current is flowing, right? So in order for the current to flow, we have to apply a positive voltage here relative to the source terminal for the current to flow. And now we will, in this specific case, we will start with what will happen when we apply a very small voltage values of the order of millivolts, let's say 50 millivolts or so, at the drain terminal. In the subsequent lecture, in the next lecture, we're also going to consider a case when we apply bigger voltages. For now, just to understand the basic operation, let's assume that we have applied just a very small voltage. So very quickly, just applying a small voltage is going to induce an electric field again in between the drain and the source terminal, right? And you have a positive charge, the electrons are going to start to flow here. So this is the flow of electrons. And by convention, the flow of the current is opposite to the flow of electrons. So our current is going to flow from the drain to the source, right? So that is why this is called as a drain current, and your source current is equal to the drain current. Okay. So let's see. So once the channel is induced again here, this means that, of course, your gate to source voltage is greater than the threshold voltage. We apply a small voltage between the drain and the source, which is this VDS. Let's assume a case where VDS is very small, 50 millivolts. The voltage causes the current to flow through the induced N channel. We talked about this. We have a charge. We have a lot of these electrons. We have some free electrons here as well, some free electrons here as well, and a channel filled with electrons. So when we apply a small VDS at the drain terminal here, the current will start to flow through the induced channel. Okay. We just discussed this thing, that the current will be carried by the free electrons that are traveling from the source to the drain. And that is why these names are coined as well, right? The source, which is the source of all of these electrons. Of course, there are the free electrons in the drain as well. But this is where the electrons are coming from the source terminal and going into the drain terminal. So that is why these terminals are also known as source and drain terminals. And then we talked about the direction of the current flow is opposite to that of the negative charge. And so the ID will be from drain to source. This ID, this drain current. Okay. So this is what happens when we apply a small VDS drain to source voltage to this NMOS. A current will start to flow, the drain current. Now let's calculate the value of this drain current. Okay, so in order to calculate the value of this drain current, we can start with an assumption, and we already started with an assumption that the VDS value is small. Again, this will become more clear why we are just even starting with a smaller VDS value and a bigger VDS value. Why do we care? We're going to realize that in the next lecture. For now, let's just assume that the VDS value is very small, which essentially means, so if you will realize that the value of the overdrive voltage or the value of the VGS, we know that the VT, in the last lecture, we know that the VT was around somewhere in between 0.3 to 1 volts, right? So even if I will, so for the gate to source voltage, or the gate voltage needs to be greater than the VT to induce a channel, and the channel is induced over here. So even if I will assume the gate to source voltage as 1 volt here, this is 20 times more than the 50 millivolt of the VDS. So we already have a very comparatively, relatively very high overdrive voltage or the gate to source voltage as compared to the drain to source voltage. And the reason why we want to make this assumption over here is that because this will help us making the IV characteristics in the next lecture. But more importantly, what is happening when the VDS is very small is the voltage in between any of these parts, and we kind of discussed this idea before. The voltage, this is positive here, right? The voltage in between the various points of the channel will be exactly the same and will be equal to the VDS because our VDS is very small. So the voltage potential difference at the source terminal and at the drain terminal between the gate and the channel will remain the same and will remain equal to VDS. We will also see what will happen when we will increase the value of the VDS comparatively to the gate to source voltage. Then we will realize that in future, in the next lecture, that the voltages in between the source at the source terminal and the drain terminal will not remain the same. Okay. So anyways, the bottom line of this specific slide is we ended up applying a smaller value of the VDS that allowed a constant voltage drop between the gate and the source terminal, which is the same throughout the channel. Due to this potential difference and application of this small VDS, a current will start to flow, and the electrons will start to flow from the source terminal to the drain terminal, and the direction of the drain current ID is from the drain to the source. Okay, so let's find out the value of this ID. Okay, so we talked about this thing again. The effective voltage between the gate and the various channel points remains equal to overdrive voltage. We just talked about this. Okay, so let's define one more thing. So what we are trying to do over here is that we have applied a smaller VDS value. Now we are trying to see, we are going to derive this value of the drain current, and we will also see on what factors the conductivity of this channel depends on after applying the VDS value as well. Okay, so how we can define the charge per unit length. So from the previous, if I will go to the previous slides, one of the previous slides, in this equation, right? So this equation can be used to define the charge per unit length. Essentially, you can take this L over here, and this will be charge per unit length, right? So going back, so the charge per unit length can be defined as this, right? So that equation was Q equals Cox WL over drive voltage. So if we will take this L over here, we can get this equation. So this is the charge per unit length. Similarly, when we apply a small VDS value, we will establish an electric field across the length of the channel. So the electric field can be given as, right, so we know that from the basic electrical engineering courses, V over D or V over L. So our voltage over here is the drain to source voltage because of the VDS electric field that is established, and L is the length of the channel. So we ended up establishing this electric field across the length of the channel by applying a voltage VDS. Let's define one more term before we will. So what we are trying to do over here is to find this ID, right? Okay, so in order to do that, we have to define one more thing, and that is the mobility of the electrons. Okay, so let's define this on something that is called as the electron mobility, mu n. So electrons will move or travel through this channel from the source to the drain at a specific velocity, which is called as a drift velocity, right? So once we apply this electric field, it will cause these electrons to move, the channel electrons or the electrons in the channel to move from the source to the drain at a specific velocity. So that is called as the drift velocity, right? So the drift velocity can be defined as mu n modulus of E, and we can use this value of E over here, VDS over L. So mu n VDS over L. So this mu n, which is the mobility of the electrons, also depends on different fabrication processes. For example, if you are fabricating a PMOS rather than NMOS, we will be more interested in the holes, which will be the mobility of the holes. And we will realize that the mobility of the holes, we're going to come back to this point again in the subsequent lectures, but mobility of the holes is smaller than the mobility of the electrons. So anyways, more importantly, these mu n factor, whether it's a mu n or a mu p, whether this or that, this will depend again on the fabrication processes or how do we fabricate the transistor, and it will be a constant in terms of your designing of the circuits. Okay, so we talked about just talked about this. Mu n is the mobility of the electrons at the surface of the channel. It's a parameter that depends on the fabrication process. Okay. Okay, so let's find out the value of the ID now. So the value of the ID can be found by if you will multiply the charge per unit length. So we have these two equations now. So one equation is this. Let me find it over here. So our one of the equations, we have this, which is charge per unit length, Q over L equals mu ox W VOV. So let's multiply this by the electron drift velocity. So our electron drift velocity is mu n drift velocity. Okay, so it will be mu n VDS over L. Okay, and we can also, so we have to find out ID, right? And we know that again, we can find out I very simply by Q over T. So at least the dimensions needs to make sense. Our drift velocity dimensions, the dimensions for the velocity is meters per second. So this dimensions will be cancelled out with this. Okay, so dimensions make sense. Okay. So we have mu ox, C ox, mu n. So one is this term. Then we have this length and the width of the channels, and then we have two voltage values. One is the overdrive voltage and one is the VDS voltage. So this is equal to the drain current, right? Okay, so this is the drain current that will flow through the channel. Okay, so this is how we can find out the drain current that is flowing through the channel. Now, as you will realize is that, so we are going to discuss all of these parameters, right? So if you have a higher mobility of the electrons, this will increase the current. If you have a higher capacitance of the oxide layer, it will increase the current. If you have a higher width of the channel and a lower length of the channel, it will increase the current. If you have a higher overdrive voltage, it will increase the current. And for now, we are just assuming that the VDS is very small. We will come back to that, how this equation will fundamentally change when the VDS will be more. Okay. So another important consideration over here is assuming now that VDS is small, we can rewrite this equation by, can I write this equation as ID equals mu n C ox. Essentially, I'm just going to interchange these voltage values. W over L, VDS, VOV. Assume this to be very small. These are constants. Once the transistor is fabricated, the length and the widths are constant in terms of a design of the circuits. Mu ox depends on the fabrication, your oxide layers, thicknesses, mobility of the electrons here, again the fabrication process parameter. So this entire thing can be a constant. So if this entire thing can be a constant, this means that I can see this equation to be a linear equation. So our channel essentially is behaving as a linear resistance. And the value of this resistance can be controlled by the overdrive voltage. As we increase the overdrive voltage, the drain current will increase. And again, the overdrive voltage is the effective voltage beyond threshold voltage. So if we are increasing the effective voltage or the overdrive voltage more and more, this will increase the drain current more and more. Okay. Right, so this is what I just wrote here. Okay, so let's define another. Of course, our VOV is VDS minus VD here. Okay, so let's define the conductance of the channel. So the conductance of the channel can be defined by, just divide this over here, ID over VDS. Right, so our GDS is ID over VDS which will become equal to mu and C ox, W over L, and V over V, right? So the conductance of the channel is going to depend on the three factors. So one factor is this, the second factor is this, and the third factor is this. Conductance is a parameter which is dependent on three factors: mu and C ox, W over L, and the overdrive voltage. Okay. So we will, in the next lecture, okay, so we are going to end this lecture over here, and then in the next lecture we are going to talk in detail about these three parameters in some more detail about this conductance of the channel. We are going to look at all of these three factors individually, and then we will establish an IV characteristics using this equation. We will write what will be the drain current, and what will happen when we increase or decrease the drain to source voltages on the for particular gate to source voltages for the NMOS. So that will be a topic for the next lecture. So before I will finish this lecture very quickly, what we talked about in this lecture, we started with the basic operation of the channel induction. We kind of covered that topic, and we started with how this thing behaves like a capacitor, right? And then this capacitor once we induced a channel, it will accumulate a lot of these electrons. And this charge accumulation, we ended up defining different features on what will happen or how we can increase or decrease the charge accumulation by changing the capacitance values, by changing the overdrive voltages. We also ended up finding different relationships for the capacitance. We discussed different parameters that the capacitance depends on, majorly the materials of the oxide, silicon dioxide here, and the dimensions of the width and the length of the channels. We also, in an example, we also determined the total capacitance for a particular MOSFET with a specific length and the width of the channels. We very briefly discussed when we apply a small VDS, the current will start to flow in between the source and the drain. The electrons will start to flow from the source to the drain. However, the drain current is in the direction from the drain to the source, opposite to the flow of electrons. Okay. Then we talked about these different factors, electron drift velocity, electric field intensity, with the intention of deriving this final equation of this current, right? And so important thing that will come up again and again is that in this equation we can see that the channel can be represented as a linear resistance when the VDS is very small, and that can change by changing the value of the overdrive voltage of the gate to source voltage. We also define this conductance formula. Okay. Okay, so in the next lecture, we're going to talk about these different parameters and the IV characteristic. All right, thank you so much, and have a good day. Bye-bye.